Hello, good evening. Can you hear me? Okay, good. Well, so today we are going to shift to the next half of the course. So we are done with the government's bonds market. That's it about it. And now the rest of the course is all about equity type securities. So we're going to talk about, well, actually equities. So generally, we're going to talk about risky securities, and therefore that will be our major topic. However, today we will not talk about equities or portfolio building. We will talk about risk aversion and utility. And so um, let me share my presentation with you. So, um, okay, I guess I need to. So where is the presentation itself? Cannot see it. Somehow it's switched off. Wait for a second. Okay, now it's should be on. So tell me please if you can see the presentation. So it's about expected utility and risk aversion. Good. So strictly speaking, it's still not about equities or risky securities. And recall that the beginning of the very first lecture in our course, actually, we never have made any, I mean, we did make some assumptions about how we behave. For example, recall that in the very beginning of the first lecture, we set two assumptions that people are risk averse. Actually, this is our second assumption. And the first assumption is that people are time impatient. And then we explain this time impatience with a poor imagination and with a sudden mortality. Therefore, and that was our major factor in the government's markets, because I recall that we always discount. So we always discounted in the previous half of the course, and that this discounting actually reflected time and patience of people. So this is our first assumption. It's going to be held with the second half of the course, obviously, because these are the same people, the same psychological property for all investors, whether they invest into stocks or into bonds. And then our second assumption was about risk aversion, but we did not exploit this assumption much. Actually, we did not use it at all. Recall that all our pricing was about value additivity, no arbitrage, and time and patience. So we did not use a risk aversion a lot, because actually when we talk about the government markets, strictly speaking, this is not really very much important. But when we shift to equity markets, or when we shift to generally the markets for risky securities, we need to take risk aversion, we need to give more attention to risk aversion, because it's not only that time and patience is present within pricing models, because obviously time and patience will always be present, will always discount within any pricing models. But then into these pricing models, which we are going to discuss next, we are going to incorporate risk aversion explicitly also, because this time we encounter risk when we invest into risky securities, and therefore risk aversion as parameter should be given in the equation in the pricing model. So it can be given either explicitly, that is, you just see it as a parameter in a pricing model, or it can be somehow hidden within the equation, but still it's there. So that's why today we will talk about just risk aversion, not about pricing models. But then, if I still have time today, we will shift or switch to the next topic. It's about the portfolio theory. You probably have studied the portfolio theory already within this master's program or probably somewhere in your bachelor courses, but we will look at this theory from another point of view, and I hope at a slightly more difficult level because we are going to use matrices again, but that's not today. So today we will just talk about expected utility and risk aversion. So let me switch on the marker and I'm going to shift to the next slide. So marker, okay, and next slide. Okay, that's what I just have already said. I remind you that this is our risk aversion. Risk aversion means that we have a trade-off, meaning that if you want more return, expected return, you should have you should agree to take into bearing more risk. If you are not ready to bear more risk, you have to be satisfied with a smaller amount of return. So this is our trades off, and there is nothing to be done about this when you invest into risky securities. Also, I'm not going to spend any more time on this slide because that is what I have just already said. And probably, well, risk aversion. Actually, risk aversion, in order to express risk aversion as a parameter, so you understand that in any pricing equations, we have dependent variable, independent variable, and parameters. So a risk aversion is going to be just one of the possible parameters of the equation. But the question is, how do we represent this parameter? So what kind of parameters that, how should we represent it? And then the answer is, first of all, we should extract it from the utility function. So if we know the utility function, then we just extract or derive the risk aversion parameter from the utility function. Therefore, we're going to talk about utility function and also risk aversion. But before we shift to the utility function, let me just give you a very stylized example of risk aversion, and probably some of you have heard about this example, but this is usually goes as this usually goes as a stylized example in many courses, microeconomics, finance, where we study risk aversion. So assume that we have some gamble. Gamble means that the outcome is not known to us, so the future outcome is not known to us. There may be many outcomes. In this particular case, we have two outcomes. So we have binomial gamble, but that's not necessarily. We might have different outcomes, many different outcomes in a gamble. Tell me, please, for example, let's look at an example. It's a roulette wheel as an example in a casino. So if even if you have never participated or visited casino, you should know, you should imagine this roulette wheel. So tell me, please, how many unknown outcomes, or just how many outcomes does a roulette wheel will have? So how many outcomes will it offer to you? So three, just three. No, not three, much more. You just count colors, but that's okay. I know that you can actually bet on either a red or a black, but these are just not outcomes. There may be actually many outcomes. What other stake can you make? You can bet on what? Yes, 37. So 36 numbers and 0. So we start with 0, and then also there will be 36 numbers. So in total, there will be 37 cells. And well, I guess you're not the only one like that. There are other students who don't know much about casino. We'll talk about it later on. But anyway, so 37 random outcomes, you don't know which number will be chosen, but so that's just an example of multiple outcome gamble. But we are going for simplicity. Simply for simplicity, we are going to talk about binomial gamble only, so two outcomes. Could you please give me an example of a binomial outcome or binomial gamble? Yeah, coin flip. Coin flip is the best example, a stylized example. So you can flip a coin, and then you will get either heads or tails, and so the binomial. So this is a binomial gamble. So we assume that there are two possible outcomes, x1 and x2, and they are random. So we can just try to assign some probabilities to these outcomes. When in case of coin flip, these probabilities are quite known. It's if the coin itself is fair, right, then the probabilities are 50% and 50%. If the coin itself is fair, meaning that if it does not have, I mean, if its weight is equally spaced all over the coin, but if the coin is not fair, then probably the probabilities will be different. But in a fair coin flip, the chances are 50% and 50%. So these are probabilities, and then you can actually calculate what is called actuarial value. Don't be afraid of this name. This is simply expected value. Actuarial name value is the same as expected value, and if you look at the formula itself, you'll see that this is indeed how you calculate expectation, or actually this is just a weighted average. So a weighted average outcome. So this is our outcome 1, outcome 2, and we just weighted with probability. So this is our actuarial value or just weighted average. And now assume that I offer you this kind of gamble that, I mean, I will offer you a choice. If you don't participate, I'll just give you for sure this expected value. And if you agree to participate, then you will either get x1 or x2, but you just don't know what you will get. Obviously, expected value is if we assume that x1 is positive and x2 is positive, well, then but x1 and x2 are not equal to each other. So just for example, x1 is less than x2, then obviously expected value will be somewhere in the between these two outcomes, but then you will get it for sure. But if you participate, you will probably get x2, which is larger, but you don't know whether you will get x2 or x1. So this stylized example usually says that if you are risk averse, you don't choose the second option. You would prefer to get this actuarial value for sure. If you are risk neutral, you would be just indifferent between taking this amount of money for sure or participating in the gamble. Finally, if you are risk lover, then you would prefer to participate in the gamble. So that's what I said, and this is what is just written. I mean, what is written here is just what I have just said, and that is our stylized example. Now you probably kind of understand more about this risk neutrality, risk loving, and risk aversion, but we're going to proceed with this. So let's now start expressing risk aversion. So this is a kind of verbal description of risk aversion using an example, but now let's try to, we will go further to derive formally risk aversion. And for this, we need to discuss the utility function. So I'll go to the next slide. Okay, so a utility Okay, I got disconnected. I guess now I'm connected once again. So let me switch to the presentation again. So where's the presentation? This one. Okay. So I put the indefinite article here, a utility function, meaning that we don't have just some I don't know, unified utility function. In fact, I don't assign any mathematical formula here. I just say that we have some utility function, and this function, this is a dependency upon wealth. So this is W means that this is wealth. So we're talking about end of period wealth, meaning that there is no need to calculate your utility depending on the wealth which you already have. We're talking about gamble. So we're trying to think what would be your utility from the end of period wealth, meaning that at the end of the gamble, you will get some wealth larger than you have, smaller than you have if you lose actually. But anyway, so that's what you are most of all, this is what is important for you, what will occur to you later, that is what kind of wealth you will get at the end of the gamble. So that's the utility of the, not just wealth, but the utility of the end of period wealth. And there is, I do not assign any mathematical formula to this utility. As you can see it, I just say that we have some utility of wealth. Why this is so? Because in fact, there might be many mathematical formulas which satisfy the definition of the utility function. And in fact, this is indeed so. There is no single mathematical equation which would be characterized as something like this is the utility function which satisfies all people. So this is just does not this does not happen, and therefore we would not assign any precise mathematical formula here. Also, mind it that this is actually a little bit from the utility theory, which itself is a separate discipline. But we are going to talk about this only within one lecture, so I try to be as brief as possible. But if we would go to the discipline, which is called the utility function or something like that, then you would probably know that utility can be modeled not only based on the wealth, but also based on other parameters as well. For example, you would probably all agree that age might influence utility. That is, when you get when you're young, you probably have some level of utility. Then when you get older, you might look differently at money from different points of view. You might have different attitudes to money, to wealth, and therefore utility can be a function of multiple variables. But again, for simplicity and because we don't study the utility theory in this course, we will model utility as a function of just only one variable. So whatever mathematical function can be described this utility function, I mean, there can be many mathematical functions, but whatever, anyway, there should be two properties which should hold for the utility function irregardless of whatever mathematical formula describes the utility function. So let's look at these two properties. First of all, the function should be increasing in wealth, which is quite obvious. The more money you have, the more the happier you are. Well, this satisfies most of people. I don't know if it's possible to find a person who is not more satisfied with having more amounts of money. So this is our first assumption, which rationally holds for the majority of people. And tell me please, how can this assumption be represented mathematically? So what should we say in mathematical terms in order to say that, in order to describe this assumption? Right. So this is just all about utilities. So a function should be increasing, but that means that the first order derivative should be positive. And let me just express it like that. So utility is first order derivative of the utility is positive. But then, as I said, there are two properties which should be held for, or which should hold to satisfy the definition of the utility function. And this is our second property. So even though the utility function itself is increasing, marginal utility should actually be decreasing. I put here non-increasing, but let's be more specific. It should be actually not just non-increasing, it should be decreasing. What it means? It means that when we get some more money, definitely we become happier. But if we, I don't know, if you, for example, have 100 pounds, for example, and you get 10 more pounds, that makes you happier. But if you have 1 million pounds and you get 10 million pounds, then probably it will, you will still probably be happier, but not that much. So you have a kind of satiation with this amount of money. That means that the marginal utility is decreasing. How should we put it in mathematical terms? Right. So, so diminished marginal utility. Yeah, this is diminished marginal utility. So the second order derivative should be negative, and let me just express it. Okay. So again, I put here for generality less than or equal, but let's be more specific. It actually should be not just non-increasing, it should be decreasing, so it should be less than 0. And then if we take into account these two properties, then the last property, the first property, will come as a consequence of the first two properties. Let me first just show you this consequence. And then we'll go into talk about this consequence, but you will see why this is just a result of the first two properties. We will see it a little bit later, but let's just look at this property. So what this third property says, it says the following, that if we have this utility like that, by the way, so how it looks like. So here we have wealth, here we have utility, so it's increasing, but it's increasing at a decreasing pace, at a decreasing speed. So this is this shape, this kind of shape. And you already see that actually we can, if we try hard, we can think of many mathematical expressions or equations which satisfy this shape. So which describe this shape. So it means that there is not just one unique mathematical formula. There can be just different mathematical expressions. For example, I believe that the function like that, y is equal to square root of x, looks something like that. But this is just one possible expression. It's not just like the only one. Well, correct me if I'm wrong, but I think that we can that this function can suit this curve. Okay, let's come to this third property. So what it says the following, that if the first two properties holds, if we have this kind of shape, then it means that the utility of not participation. So you see here, you prefer not to participate and get the expected value of the gamble, or actuarial value of the gamble for sure. So you don't participate, you get the expectation for sure, and then you get some utility of these amounts of money. And here you actually prefer to participate, and then you don't know what kind of amount of money you will get in the future. That means that you don't know right now what kinds of utility you will have in the future. But right now, as long as you know probabilities of each outcome, you can calculate the expected utility. So again, that will be a weighted average utility. So there will be two possible utilities in the future. You don't know which utility you will get, but you can calculate expected utility. And therefore, this is not participation and having money for sure. This is participation, And therefore, so this is the utility from not participating, and this is utility from participating. And if the utility function, if your utility function takes this form, shape, then it means that for you, it's always be like that. Your utility from not participating will always be larger than utility from participating. And because of this, because you have larger utility if you don't participate in the gamble, that means that you will always choose not to participate in the gamble because you will get larger utility from this. And first of all, we'll look at the example, it's an example, and then we will see graphically why this holds true. So why this is so. So let me move to the next slide. And this is just a very simple example. So assume that we assume that there is an individual, for example, some of you, and the utility function of this individual can be described as a log function. Now, this is how the log function looks like, but probably you can recall it from. Okay, there is just one question. What is the difference here between round brackets and square brackets? No difference. There is no difference between square brackets and round brackets. I just don't like the situation. I don't like formulas where we have many brackets like that. I would prefer to alternate square brackets and curly brackets, just like that. Okay. Okay, so you can recall probably from school that the log function looks like that. Don't be confused. In this, we have some negative area here. So what is less than 1? The values of the utility. So this is our utility. This is our wealth, and we have negative utility here. But don't be confused by this because actually utility is not really measured. It's just a question how to measure happiness. There have been some attempts to measure happiness, but that's right now there is no unified definition what units of measurements of happiness we should use. And actually that's why a general convention is that utility is has no unit of measurement. So this is a cardinal number. Cardinal means that we just have numbers, for example 1, 2, 3, etc. And we just know that 1 is less than 3, and therefore this utility is smaller than this utility. And that's just like that. So -4 just means that here we have smaller utility than somewhere here, and that's it. So it just doesn't measure whether it's negative or positive. Okay, and so I remind you that if we have the first two properties to hold, then our utility from not participating will be larger than our utility, expected utility from participating. Once again, it's expected because this is what we know for sure. I mean, we can always calculate expectation now. We don't know the true outcome because it will occur in the future, but we can always calculate expectation now. So that's why the utility from not participating is known to us right now. But as for the utility from participating, we right now can only calculate expected utility. So this is what we are going to show that is going to hold. So here I have just some numbers of wealth. So you can measure it whatever you like in pounds, in thousands pounds, whatever. Anyway, so here we have 1, 4, 10, 28, and also we have the for this level of wealth, we can assign a level of utility. So just like you calculate logs of these numbers. And now assume that the binomial gamble in which you participate will give you either $4 as outcome and the chance for this is 75%, or you can get much more, $28, and the probability of having $28 is smaller than the first probability. It's only 25%. First of all, let's calculate how much would I offer to you if you don't participate in the gamble. So this is something like you can get for sure. We calculate just average or actuarial value as a weighted average probability, and well, actually probability weighted average. That's the correct name, and this is going to be equal to 10. So your utility, not your utility, the amount of money which you will get, which you might get for sure is $10. And then we can easily calculate what will be your level of happiness, your utility of getting this amount of money. Again, it has no units of measurement. This is just 2 points free. Now, if you choose to participate, then you will either get 4, and then you will get some utility of 4, and you can calculate this utility by just putting log here. So this is log. Or you will get 28. Again, you can calculate a log here, and that will be a utility. But you don't know what you will get because that will occur in the future. And therefore, right now, you can only calculate weighted utility, weighted average utility. So you weight by probabilities, and then you get 1.9. And indeed, you see that 1.9, but like that, 2.3 is larger than 1.9. So your utility from not participating will be larger than your utility from participating. And therefore you will not, if you are risk averse, and probably I did not mention this, this kind of shape, so how we call it, increasing function with a decreasing speeds. So this kind of shape, okay, actually it's concave shape. That's what the right word. So not convex, but concave. So this is concave shape. And so this concave shape represents as someone who is risk averse. So it's not for risk lover. The shape is not for risk lover. It's not for risk neutral. This is precisely risk averse investor. So this concavity means a risk aversion. And we already see that indeed this person is risk aversion because under this concavity, his utility from not participating will be larger than his utility from participating. So he will never choose to participate in a binomial gamble or any kind of gamble. So if we want just to be general, so he would prefer not to participate. This is a risk aversion. Now my question to you is, so this is question. So you already see, well, you already know something about the utility function. There are lots of interesting things about it. But do you think that, so the question is, okay, risk aversion as a parameter is given, is incorporated into pricing models. So this is something, half theoretical, half practical, because indeed we develop pricing models in practice, but then in theory, but these pricing models are used in practice. However, are there any cases where we could use precisely risk preference or risk aversion, degree of risk aversion, or attitude to risk? It's just all the same: risk preference, attitude to risk aversion. So are there any practical areas where we just precisely use risk preference or risk aversion as a notion in some, probably in some practical fields? What do you think? Okay, can you give me an example where we can, where it is utterly important to know something about person's risk aversion? Okay, so Victor suggests that it's about creating portfolio, and Maxim suggests attracting LP for venture capital funds. And what is LP, by the way? I don't know. Mm. Mm-hmm. Okay, I'm not sure about this because I don't know. I mean, I don't know whether this is something like very, if this is obligatory to to find to find risk aversion of a limited partner. I don't know. But if you know about this, you could just probably say something about it, but or write something about it. But as for funds clients and creating portfolio, indeed this is an area. I'm not sure whether you mean what I would like to hear, but let me just continue with this. So if you well if you are a client and if you have a portfolio manager, then your portfolio manager should before this portfolio manager creates a portfolio for you, he or she should first find out your risk aversion coefficient. If this is not done, so if the portfolio manager offers you the portfolio which is not consistent with the level of risk of his clients or her clients, then that's not just something like a bad practice. This is something illegal. And this held true for most countries, at least I don't know, in Europe this is like that, in the USA this is like that, and in Russia this is also like that. And this is, well, obviously we adopted this rule, this law. Well, this is not it does not have the status of law. This is something which is a recommendation by the central bank. But you know that recommendations of the central bank means something like very obligatory to perform. It's not just a recommendation as we might think. And therefore, actually, if you don't do this, if you are a portfolio manager and if you offer a portfolio to your clients without finding out his or her risk aversion, then you will be accused of something which is called mis-selling. So selling means, well, sale, продажа, and mis means, you know, there's something that you're doing something wrong. So mis-selling. Mis-selling, and this is actually, I don't know, what will happen to you for this. I mean, I asked once like my broker what would happen to him if he offers me a portfolio which is not in line with my level of risk, and he said that at least he would be fired if it would be like that. So the tangent joints of, I guess this is capital allocation line and utility curve is the optimal portfolio for clients. Okay, Zhao, this might be true, but this has nothing to do with the risk aversion, really, because optimal portfolio has nothing to do with risk aversion, and we will talk about this. Well, not today. I think next time you will see this. Anyway, so once again, finding a risk preference or a risk profile of your clients is obligatory. And first of all, this holds true for wealthy clients, but even like I have my personal financial advisor. But I mean, everyone who has brokerage accounts is assigned a financial advisor. So I'm not that much importance probably for my broker, but still I have been assigned a personal financial advisor, and I have to pass a certain test in order so that they could just reveal my degree of risk aversion. So this is something obligatory. Okay, let's move further. And so that's it for this slide. And once again, look here. So this is what we are going to stick to. So this is our major parameter, major description for risk aversion. As a result of risk aversion, you will always choose not to participate rather than to participate in a gamble with random, unknown random outcomes. Let's see how it can be explained now using geometry. So recall once again that if you are risk averse, then the utility function is going to be this is going to have this concave shape. So now this is not a log function. This is just some function which has not log, concave shape. So not necessarily log function. So this is our utility. Here we have wealth. And now let's assume that the binomial gamble is actuarially fair. Actually, this is more realistic because it would be really weird to have a situation when I offer you either positive, like here, yes, I offer you some positive amounts of money if you don't participate, but if you participate, you will get either these positive amounts of money or these positive amounts of money. This is too good to be true. You know that usually in a binomial gamble, you can either win or lose, so it's not possible that you will win and win. Therefore, this situation is too good and you will never encounter it. So a more realistic situation, though problem we'll talk about it's how whether it's realistic or not, but let's just for simplicity look at this situation. So on average, so the actuarial value is actually equal to 0. So this actually means that the gamble, binomial gamble, is fair, actuarially fair. That is, on average, you neither win nor lose. On average means that it means that on average you are left with what you already have before I offer you this gamble. So what it means, if this is going to be equal to 0, it means that x1 should be negative and x2 should be positive. Otherwise, or x2 should be negative and x1 should be positive. Anyway, one outcome should be negative and the other outcome should be positive. Otherwise, you won't come to 0. So this is more realistic. You either win or you lose. And so that's what we have. And now let's look at this gamble. And I remind you that again, your risk aversion still suggests that you would prefer not to participate and stay with the amount of money which you already have, rather than you would participate and you would either lose. In this case, your amount of money will be smaller than you originally have, or you would win. In this case, your amount of money would be larger, but then the question is whether you will win or not. So let's assume let's assume for simplicity that x1. So this is our bad outcome. We lose here. And we assume that x1 is equal to x2 in absolute value, meaning that like that. So meaning that, for example, can be -5 and +5, -10 and +10. Again, and also let's assume that chances, so if they are equal to each other in absolute value, then in order to get 0 here, we are bound to have probability equal to 50% here, and this probability is also equal to 50%. Otherwise, we won't come to 0. Well, generally, you can alternate this situation. You can assume that x1 is less than x2 or just in absolute value, or the other way around, but then you just need to adjust probabilities in order again to come to 0. But if we assume this equality, then we will have a symmetric picture. That's what we have here. The graph here is symmetric. If we assume that they are not equal, then just the graph will not be symmetric, but however, that just doesn't change the general results. I would like just the graph to be symmetric because it looks nicer, it looks better. That's just the only reason. So your initial wealth is W0. So actually this bar, you can see this bar here. This bar means that this is an average value, but actually this is your original value. And if you lose, then you will lose this amount of money from your original value. If you win, then you will add this amount of money to your original value, original wealth. But if you prefer not to participate, then you will get for sure a 0. So that's what I will give you for sure, the expected value, which is equal to 0 in this case. And that means that you are just left with the wealth which you already have. So this is your original wealth, or let's call it just average wealth, because here we have just average. What else? And now let's assume that as a risk-averse investor, or well, you're still not an investor, you're just an individual, and I offer you a gamble, not investments. So you, as a rational individual, as a risk-averse rational individual, you prefer not to participate, and therefore you are left with what you already have in terms of wealth. And I can read up, and then I will read left, and then that will be your level of wealth if you choose not to participate. So this is your level of wealth, like that. But now, if you choose to participate, then it depends on what outcome will occur. So assume that this is bad outcome. Well, this is bad outcome, and this is good outcome. So if bad outcome occurs and you lose money, then again, we can read up to this point and read left, and then your utility will be at this point. If good outcome occurs, then your utility will be at this point. You don't know which utility actually you will get if you participate, because you don't know the outcome which will occur. But let's look at these 2 points, point A and point B. So point B corresponds to good outcome, point A corresponds to bad outcome. So at this point, at point E, it's just like as if bad outcome occurs at the 100% probability. So you are at this point. So 100% probability for the bad outcome. There's if you are at this point, then there is no probability for good outcome. So this 100% probability for bad outcome, like that. And if you are at point B now, then actually this is where a good outcome occurs. So here we have just 0% probability for bad outcome, and so it's totally good outcome. So 100% probability for good outcome. So then what do we have when we connect points A and points B with a line? So this is our straight line. So this straight line, if we move from A to B along this straight line, it is as if we slightly decrease 100% probability and increase 0 probability. So we do this, and then we slowly come to point B, where we have 0 probability for bad outcome and 100% probability for good outcome. So essentially, the line represents different combinations of probabilities. So we decrease probability of bad outcome and increase probability of good outcome. So essentially, this is just a weighted average, probability weighted average outcome, like that. So probability weighted outcome. But we know that if we have symmetric picture, then our probabilities are 50% and 50%, and therefore we're supposed to be somewhere in the middle of this line, so somewhere here. And at this point, so this is essentially so this is our utility from bad states, which occurs with 100% probability. This is here we have utility of good states, which occurs with 100% probability. Then somewhere in the middle we have 50-50. So it's expected, so average, weighted average utility were weighted by 50% and 50%. And then we can actually find the level of the utility. So this is our level of the utility. And now we can compare. So this is utility from not participating, and this is utility from participating. So you see that the utility of not participating will be larger, always larger than the utility of not participating, meaning that this curve line. So this is curved line. So this segments, I'm sorry, it's like that. So this segment is curved, and this segment is straight line. And well, I hope you can distinguish this. So if we have concave shape, then the curved segments will always be larger, higher than the straight line. And that's why utility of not participating will always be larger, because it lies on the curved parts, not on the straight parts. So for the concave function, the utility of not participating will always be larger than the utility of participating. And therefore, this definitely is a risk aversion. So we can say that a risk averse individual is always featured with a concave utility function, so that there is no other way around. Well, I guess that's it for this slide. And now, yes, now, so the same picture here, we already talked about this concave function, and we already know that these segments, curved segments, always lies higher than the straight line, and so this correspond, and this means that utility of not participating will always be larger. Now, let me check if you understand this. So so this is risk aversion. We're not going to discuss risk neutral or risk lovers. However, let's just specify, if we're talking about a risk neutral investor, tell me please, how would a utility function for a risk neutral investor look like? What kind of shape will it take? So this is my question to you. Oh, okay, I'm sorry, I just got somewhere here. So for a risk averse investor, this is a concave curve, concave function, concave shape. What's about risk neutral investor? Right, so this is going to be a straight line. Let me just draw it first of all. Exp. What is exp? So anyway, but what is exp? Exponential, you mean, or what? Exponential. Could be. Okay, could be just one of possible mathematical equations, yes. Anyway, so I'll just draw the straight line like that. So what we can say, in this case, the utility is increasing. It should be increasing, obviously, because anyway, whether we are risk neutral or risk averse, we still love more money than the situation with more money than the situation with less money. But this time, the second, so the first or the okay, let me just put it. So the first of the utility is positive, right? But the second of the utility is equal to 0, meaning that the function is increasing at constant rates of growth. So there is no diminishing rates of growth. There is a constant rate of growth. So in this case, so this is our utility of not participation. From not participating, this is our utility from expected utility from participating, and now they are equal, because even if we just, I don't know, any 2 points which connects, I mean, any line which connects any 2 points will be a straight line. But since the utility function itself is a straight line, then the segments of the function will coincide with the line. So that's why our investor or our individual will be indifferent, because here the line does not coincide with the curve, but here it will coincide. And a risk lover, as it just was already said, exponential, but not necessarily exponential. It's anyway, it should be, it will take this kind of shape. Okay, like that. So this is our risk lover. So this shape, so if risk averse has a concave shape, so this is concave shape, then this shape is convex. So, and in case of convex utility, again, we can just choose 2 points and try to connect it with a straight line. And let's try to do this. Okay, something like that. And for a convex function, the straight line will always lie higher than the curved line, and therefore utility from expected utility from participating will be always larger than the utility from not participating, and that's just what we have here. So that's what I have just already said, and for that's why a risk lover will always prefer to participate, because his utility from participating, so this expected utility which represents which is given by the straight line, that this utility will always lie higher than the curved line itself. So like that, I think that's it about geometry, and now let's move further. So let me see what else we have here. Okay, so so we already know that the majority of people are risk averse, and we already know that if we have fair gamble means that on average you neither win or lose. So if we have a fair gamble, then a risk averse individual would not participate in this gamble. That will not be his choice. And then let's ask the question. So this is about risk premium. So we're gradually moving to the stock market. So, but we're still within, the notion of a gamble. So the question is how to induce our individual to participate in the gamble. If he is risk averse, he would not choose the participation in the fair gamble. So what can we do in order to induce our individual to participate in a gamble? And then let's assume that we need to give him a kind of compensation. So I can say like that: if you participate in the gamble, I will give you additional amounts of money. Whether you lose or win, whatever outcome would occur, I will just give you some additional amounts of money. And let me call it risk premium, so compensation for taking risk, because if the individual participates, he takes a risk. So this is Greek letter, it's called rho, and this is going to be constant. So I'll give you the same amounts of money whether you will lose or win. So in this case, your final wealth is not like that. Your final wealth is what you get if you participate. And again, that might be either good outcome or bad outcome, but then you will also get this constant amounts of money. So that will be your final wealth. It's still a random, because even though it's constant and you already know this amount of money, but this outcome is random. So the total outcome after this kind of adjustments is still a random variable. And so now what we have, let's calculate again expected value of this wealth. So that's what you will get. So on average, so the average outcome of the gamble will be, again, the average outcome of the original gamble without risk premium plus this risk premium. Now, recall our condition for the risk-averse individual. He would always prefer not to participate because his utility from not participating is larger than his expected utility from participating. And once again, expected utility, I say expected utility because if you participate, you will know your utility only after you have participated. So right now you can only calculate the expected utility. And so the question is, okay, risk premium, kinds of compensation. But the question is, how much money should this compensation consist of? Meaning, how big this value should be. Obviously, it should be a fair value. Fair meaning that it should not be too much, because in this case, the individual would be willing to participate. That should not be like that. And at the same time, this compensation should be enough, quite enough, to induce the individual to participate. So that we should not give him or her too little. So the question is how to define this raw, meaning what amounts of money, what precise amounts of money it should be. So, and then the natural answer is we need to adjust these amounts of money in such a way that his two utilities from participating and not participating will be the same. That is, instead of this sign, which is more than, we actually put equality sign. So this is the equality sign. And so we need to add this amount of money, precisely this amount of money, in such a way that he would be indifferent. He would be on the edge between participating and not participating. So this is if he participates, so that will be his utility, expected utility. And if he does not participate, then obviously no one will give him this amount of money. No one will give him premium because there is nothing, nothing for which he would have this premium. And so this is his utility from not participating. And then it should be, this time, it should be equal to the expected utility from participating plus premium. So this is obviously equilibrium condition, meaning that equilibrium means that, well, our individual is on the edge between participating and non-participating. And also, this is implicit definition. So obviously, this is a definition of risk premium. So it's the amount of money which makes two choices, participates, two options, participate and not participates, identical from the point of view of utility. So, but why it is implicit definition? Because even though we see this formula, it's not quite understandable how to calculate this raw. So how to get numeric value for this raw. We just see this kind of equation, but then the question, how should we understand how to get the quantitative assessments of this of raw of this risk premium. So in order to find this, we need to get another definition of risk premium, which is now explicit definition. Explicit definition will tell you the formula. That is, it will give you the formula which we are going to use in order to calculate risk premium. So let's try to derive this formula right now. And I guess I will move to the next slide. And in order to derive the risk premium, in order to get just the formula for the risk premium, which will tell us how to calculate the risk premium, we are going to use our tool, mathematical tool, which we have already used several times throughout the course. Well, at least once we used it definitely when we calculated some durations. I'm not sure if, but okay, but at least once we already used it. And Taylor series is a very nice application for in many areas. And so now there's another example where we are going to use it. So we are going to use Taylor series approximation up to the second degree. So this is going to be not second degree, second order, I think, second order Taylor series polynomial. And I remind you that this is the general way how the Taylor series approximation looks like, and I abridge this formula up to the second order. We don't go any further because otherwise the formula would become complicated. So let's just be satisfied with the second order approximation. So what we are going to approximate? we're going to approximate this function. So this is our utility function. Once again, utility can be a function of many variables, but for simplicity, and the major variable, well, even if we can model it as a function of many variables, anyway, the major variable, the most important variable is going to be wealth. So this is just wealth plus premium, but this is just wealth, amounts of money. And we're going to approximate this utility about what points or around or about what points. We're going to approximate it about our average wealth. Recall that this average wealth means that the expected expected outcome is equal to 0. We have fair gamble, expected outcome is equal to 0. So if you choose not to participate and get simply expected outcome, then you will get 0, and on average you will be left with what you have already with you. And so let's now see how to approximate it. Okay, so this is our utility. Then this is our function itself. Then this is our first order. Like here we have first order. Here we have second order. So here we have also second order. And this is just squared distance. And this is just distance. So something like that. Now recall that when we're talking about utility of a gamble, we're talking about actually expected utility, because we don't know the utility, what utility you will get in the future, because the outcome is random. Therefore, let's take expectations of the left-hand side of the equation and right-hand side of the equation. So here we have just summations. And you know that the expectation, so we can take expectation is a linear operator, so we can just take expectation of each parts of this summation. So we take the expectation of each term. So that's just how it looks like, expectation of the left-hand side and expectation of the right-hand side. And now let's see whether actually we need to retain these expectations always, or we can actually get rid of some expectations. So let's look, for example, here. This is the amounts of money which you already have. Therefore, you already know the utility of this amount of money. So this is a constant. This is a variable which is known to you already. And you know that the expectation of the constants is just the constant itself. So no need to retain expectation. Let's just write it like that. Now, here, so we have expectation here, but then we can just open the brackets here and take expectation of each part. Now, again, this is amounts of money which you already have. Therefore, its expectation is equal to itself. And this will look like that, right? This is W, and this is equal to this one. So therefore, we can just remove it, and then we're just left with a row here. Now, as for this term, obviously we have, as you can see, we have square here, so we just cannot take expectation of this square like that. We need to open the brackets. And when you open the brackets, you can manipulate with this formula a little bit, and a nice thing about this will be that as a result you will obtain variance. So as a result, instead of this expectation of squared term, you will get variance. Well, how to get it? I think it's given in lecture notes, so I just don't want to explain it here, because this is something which you are supposed to understand yourself when you just read lecture notes. But anyway, so this is our results, and let's see what else we can do with this. But for this, we need to move to the next slide. And so I'm going just to take this formula, take these two formulas, and transfer it to the next slide. Okay, so this is our two formulas just from the previous slides. And now let's try to see how to, I remind you that's what we need to know. We need to get some expression which will help us to calculate risk premium. So something like that. Risk premium is equal to and some formula. So that's what we are going to obtain. And in order to obtain this, let's come back to our equilibrium equation. So we need to find rho, we need to assign some numeric value to the risk premium in such a way that our utility from not participating will be equal to our expected utility from participating. So if this is our equilibrium condition, so recall that that's the left-hand side of this equation, this one, actually it's the same as we have here. So, and if we assign equality sign here, then let's substitute the left-hand side of this equation here, here, with this one. So essentially we'll write like that here. So what we now have? Two identical terms in the left-hand side and in the right-hand side. So they can we cancel them out. So here we get 0, and here we get this. Okay, so let's see, like that. So let's now try to simplify it somehow, because here we have quadratic term. Mind it that actually we need to find rho. So we need to find how to calculate rho, how to get numeric value for the risk premium. And therefore here we have, so if you look at this is simply a quadratic equation. So this is an equation which is quadratic in rho. So if you don't see this, just substitute x instead of rho, and then that will be just an equation like that. Okay, and it's equal to 0. So this is a quadratic equation. Obviously, you know how to solve a quadratic equation. This is not a problem. And you can, if you solve a quadratic equation, you will get two roots. I guess you all know this. And by the way, in this particular case, one root will be positive and the other roots will be negative. Why so? Because if you look at the terms, at each term of this equation, you'll see that we don't have any negative number here. Risk premium should be positive. Utility, first order utility is, but actually second order utility is negative, so it's not clear whether we have, oh, I'm sorry. Second order utility is going to be negative, therefore this term might be negative, right? So, well, in this case, I guess I need to think a little bit more about this. I think in this case, it's quite possible that you will get, I'm sorry, it's different. Actually, if we had only positive terms here, then we would get one root positive and the other root complex, as far as I remember. But here we have one negative term, so therefore you will get two roots. Hopefully, I need to check for it, but hopefully one roots will be negative and the other roots will be positive. And that means that you will definitely choose the one root which is positive, because risk premium cannot be, like logically, risk premium cannot be negative. So, I mean, if you say your individual that you will actually take away money from him if he participates in the gamble, then he will, moreover, so he will not participate in the gamble. So obviously we need to offer him positive risk premium. So in this case, you will just choose the root which is positive. However, let's make it actually linear. So this is quadratic equation, but I don't know. You can actually have it quadratic, but if we refer to the original article, which was written several decades ago, and probably you have heard about the authors of the article. So this is Dobro and Arrow. Well, definitely I heard about Arrow, but there are two authors, two independent articles with the same results. So what they did actually, they decided to remove quadratic term because they wanted to have it linear for simplicity. So the linear equation will give you just a linear result, linear solution, which is much simpler than quadratic solution. So they decided they actually remove rho, and we have some grounds to remove it, because if we approximates about so we approximate, so it's about this value. So this is a very small distance, and when we square, that's going to be even smaller, and therefore we can just remove it because square roots of a small number will be even smaller, so we can just neglect it. Well, again, probably when we neglect it, we make our approximation less, even worse. But then the question is, should we be more precise but have more difficult formula, or we can just be satisfied with the linear equation. Anyway, the original articles gives us linear equation, so we can just remove this quadratic theorem, and then we have linear equation. Let's just assume that we remove it, and then we have linear equation, and then we just solve for rho. So we solve for rho, and this is gonna be our equation. So this is our explicit definition in order to calculate in money terms. So this is just a question about money terms, about how much money we need to offer. So in money terms, risk premium can be calculated like that. Variance of the future wealth, again, if this is a binomial gamble, then this will be a spread, and if there are many random outcomes, you calculate variance as you usually calculate variance, as you do it, for example, in econometrics. And then you have variance, actually you divide by 2, so half variance, and here we have second order utility divided by first order utility. So how much time do we have? Okay, I'll just, I would like to finish this slide, so let me take a couple of more minutes and then we will have a break. So here we have something like second order utility divided by first order utility. Mind it that second order utility is negative, because if we have the shape concave, then second order utility is negative. And this first order derivative will be positive, but then we have this minus here, which comes from this expression. So when you multiply by -1 the negative second order utility, then eventually you will come to a positive number. So risk premium is bound to be positive. But let's look at this, well, before we look at this expression, let's just make some logical conclusions. So risk premium is dependent upon variance. So, and it is dependent upon this expression. So variance, obviously the larger the variance, the larger the risk premium, which makes sense. Obviously, the larger the uncertainty, the larger the variance, the larger the dispersion. I'm not sure. The larger the variability of different random outcomes in the future, the larger the uncertainty, the more premium you would require, which is quite obvious. And as for this, so the larger the second order derivative, the larger the premium. But actually recall that first order derivative is the straight line, it's actually slope. Okay, let's assume that one of this line represents a slope, but then the second order derivative actually represents a curvature, a degree of curvature. So the larger the curvature, the so like it can be like that, but it actually it can go, I don't know, like that. So here we have larger curvature. So the larger the curvature, the larger. So the larger the curvature, the larger the degree of risk aversion, actually, and the larger the risk aversion, the larger the more risk averse the person is, the larger premium he will require. And but actually we're talking about not just second order derivative, we are talking about second order derivative divided by first order derivative. So it's not just curvature, we divide curvature by slope. So let's call it normalized curvature. So not just curvature, but normalized curvature. That probably sounds better. And as I said, this is something about risk aversion. So this parameter actually together with minus, so includes minus into this expression. So together this expression represents risk aversion. Finally, we have come to something which represents risk aversion. So this is our risk aversion, and we can say the larger the risk aversion, the larger the premium. And the last question is, actually, this expression, as I said, this is actually how we calculate risk aversion. And actually, it's called coefficients of absolute risk aversion. And now listen attentively, because I'm going to ask you a question. So absolute risk aversion means measures how risk averse you are if there is a bet on an absolute constant amount of money. So once again, we bet on a amount of money which is expressed in absolute terms, not in percentage, but in absolute terms. For example, $50. And so this coefficient represents your reluctance. If you are risk averse, so it represents your reluctance to participate in this kind of bet where the stake is a constant absolute amount of money. And now my question to you. So we know that utility is a function of wealth. Therefore, first order derivative will also be a function of wealth, and second order derivative will also be a function of wealth. Therefore, the ratio of the second order derivative by the first order derivative will also be a function of wealth. So this is just, well, we can just write like that. This is a function of wealth. This is function, and here we have wealth. And now my question to you, you know that function can be either increasing in wealth, decreasing in wealth, or constant in wealth. Tell me please, how do you think? Kara, by the way, this is called Kara, not Kara, not Sarah. This is just Kara. So how do you think? What would we normally expect, or what would we expect from a rational, normal, not insane, normal individual? Would he be? Would his function? Would his Kara be increasing in wealth, decreasing in wealth, or constant in wealth? So think carefully and try to answer this question. Okay, increase in wealth. Do we have other opinions, or the rest of the students think the same way? Okay, now we have two opposite views: increasing in wealth or decreasing in wealth. Another question is which answer. The one answer is correct. I wonder, in order to understand which answer is correct, you just need to switch on logic. So as there is an excess of capital to participate in I'm sorry, I don't understand what you're talking about. What there is an excess of capital. Okay, now two people believe that the function should be increasing in wealth. So let me just say it once again. This parameter represents your risk aversion, that is how averse you are to participate in bets where a constant amount of money is at stake. So this amount of money does not change, it's just constant. But we now change wealth, we increase it, decrease it, and see how Kara changes. So the correct answer is actually was given by Victor. However, I wonder whether it's just a guess, or he could explain his conclusion. Wow, that's pity. Okay, I guess you won't cope with this without an example. Assume that you have 100 pounds. That's it. That's just your wealth. You don't have anything else. So, okay, I'm just talking to you now. I think the more wealth person have, the more chance there is a person will participate, I guess. But why? Maybe if return bet is constant, we can calculate it. Kinds of, okay. Okay, kinds of. So tell me please, assume the situation that because risk is not that significant when bet is constant. Exactly. I mean, you can just calculate it as a return, and then return will be smaller, smaller, and smaller, or your loss will be smaller, actually, if you lose as we increase wealth, or because when you increase wealth, this constant amount of money becomes less and less significant. Good. Now, both of you have given correct explanation. So still, let me just come back to this example. Assume that you have 100 pounds and you don't have anything else. And I say, let's gamble. I'll give you, if you lose, I mean, if you win, I'll give you additional 50 pounds. But if you lose, I'll take away from you 50 pounds. So tell me, please, would you participate in this gamble? And you are risk averse. And you just have only 100 pounds and nothing else. And you still need to, I don't know, to feed children and to feed your wife. So would you participate? So no, you would not. No. Okay. Good. Now, assume that suddenly, or not suddenly, but you don't have 100 pounds, you actually have 1 million pounds, and I still offer you the same bet. Once again, the same amount of money in absolute terms is at stake. So you have 1 million pounds, and I offer you the same bet. So if you lose, you will, I'll take away 50 pounds from you, and if you win, I'll give 50 pounds to you. So would you now participate? Yes, exactly. So simply because it just doesn't that much importance, 50 pounds plus or minus when you already have 1 million. So that means that Skara is actually decreasing in wealth, and that's what would we expect under normal situation for adequate rational individual. As his wealth increases, his Skara decreases. Obviously, we can try to find some weird people, freak people whose Skara is probably increasing, but I just cannot imagine what kind of people, what kind of person would that be, and how would he be motivated? I just cannot imagine this. And actually, this thing, the fact that Skara is decreasing. By the way, Kara is decreasing means that the first order derivative of Kara is negative. So this kind of thing helps us to explain something which we can observe in real life. Two things. One thing, I think I'll take just 2 more minutes from you and then we'll have a break. One thing, hedge funds, it's about hedge funds. You probably know that hedge funds do not offer common people to participate. They offer to participate only a limited lists of wealthy investors. Institutional investors, that's a different thing. But as for individual investors, then only wealthy individual investors can participate in hedge funds. Why so? Because if there is a loss, then an average investor would not survive this loss. But a wealthy investor would probably agree to participate because these kind of investors have more money. They are more, they are there will be less pain for them if they lose certain amounts of money. And so that helps explain why hedge funds are designed only for wealthy individual investors, not for, I mean, if you can participate in the funds of hedge funds, but you cannot participate in the hedge funds, in a hedge fund. And another thing, this decrease in CARA helps to explain something about some insurance business. Have you ever heard about business, such business like insurance of insurance companies or insuring insurance companies? So have you heard about this kind of business? Okay, so in Russian, I think we say перестрахование or something like that. So as you might understand, insurance companies insure people and organizations, but actually insurance companies also would like to be insured themselves, because if just some contingency occurs with an individual person, then the insurance company will pay money, but the probability of this contingency is very small. But even if it occurs, then okay, the company will make compensation, but then it still have lots of money from policy, from selling insurance policies. But sometimes, but if another kind of contingency occurs, like not individual contingency, but overall contingency, for example, earthquake, tsunami, something like that, then the insurance company would have to make massive or mass payouts. You know, not just individual payouts. So insurance company would like to be insured against these kind of contingencies. Their probability is really small, but if the probability will be realized, then the company would have to make big payouts. And so an insurance company would like to be insured against this kind of contingencies, but not so many other companies would like to insure this kind of contingencies because they don't want to bear this risk. And so this decrease in CARA might help to explain why some time ago Warren Buffett was in this business. So actually, well, not him personally, but for his company, what's his name? It's Berkshire, right? Berkshire Hathaway, something like that. So some time ago, I'm not sure about now, but some time ago, his company was in this business to insure these insurance companies. And Warren Buffett actually said it explicitly, something like in one of his interviews, he said something like, he did not say he said, we have reached this certain of risk aversion where we can insure insurance companies. So actually that can be explained by his decrease in CARS. So the amount of money which he has makes him less risk averse, and he actually can afford to participate in this risky business. It's just like in the case with hedge funds. So our lecture is not over, but now we're going to have a break for 10 minutes. So now I have 10 minutes past 8. So 20 minutes past 8, we will resume our lecture. And now let's have a break. So I will stop the demonstration for 10 minutes and we have a break. So is everyone here? Shall we continue the lecture? Okay. By the way, somehow I have switched off the presentation. Let me switch it on again. Так, демонстрация экрана. Okay, so we have talked about coefficients of relative risk aversion, CARA. So now you know that it can be used in practical application to explain some practices in investments. However, up to this point, we talked about gambling. That is, we tried to explain utility and risk aversion based on gambling, as if you are in a casino. However, now let's move to from casino to the stock markets. And from gambling, we move to investments. From casino, we move to the stock markets. Okay, like that. And the question is, obviously, actually, if I mean, the mathematics of risk aversion, the mathematics of utility is the same for gambling and for investments. Otherwise, I would not use gambling as an example, because what sense in using gambling as example if now we need to switch to another kind of mathematics. So the mathematics is the same, no major changes. However, we still can try for our own purposes, we can try to draw some differences between gambling and investments from the points of view, of all these things which we just discussed. So this is my question to you. What is, in your opinion, what are major differences between gambling and investments? What do you think? So do you have any ideas how we can differentiate between gambling and investments? Obviously, investments, just like gambling, will offer you a random outcome. If you invest right now, you really don't know what return you will get in the future. So it's still random. And that's why mathematics is the same for the utility function for risk aversion. But can there be some differences? So either a loss, either or win, but that's just like between in gamble and in investment, this is just the same level of certainty. You have to explain this. Investments preserve value, like stocks, for example. Even if they drop, they cost something. In casino, you either win or lose. And this is something just, the opposite. Gambling is not always results in cash loss. But actually, why don't you think that stock can become nearly zero? Meaning that, well, the company is just a terrible disaster, and then the stock is just worth nothing. Probably very small probability, but still, quite it might happen. The company has got bankrupt, and then if it has some debts, especially senior debts, then probably it might cost something. But if this is equity, then its cost is just zero. We can explain parts of volatility of investments and make a forecast. Well, it can be absolute bets if we're talking about gambling. So, this one we can explain. In case of investment, it always involves real money. So that's what I like. Gambling is for short-term plan. This is what I like, and and something like we can explain parts of volatility of investments and make a forecast. Something like that, which we can actually develop this sentence as well. So and we will, but since I do have something in this slide and the first points which you actually neither of you has mentioned, so let's just me represent the first points, but then there will be other points that I guess we can just develop, expand on what you have written here. So the first points actually you did not mention. So tell me please, if you probably know about casino, do you on average, do you win in casino on average, or do you lose in casino on average? Right. All casinos, all casino gambles. Okay, so all casinos are structured, or gambles are structured in such a way that on average you lose. Otherwise, there is no business in casino. And that means that the expected value, so if on average you lose, the expected value is negative. It's not like what we have here, fair gamble. So where is our fair gamble? Oh, no, not here. This one. So here we have fair gamble. On average, you have 0. But in casino, on average, you lose. So actually, you will have like that. So less than. And therefore, it actually means that casino offers you negative risk premium, right? So we can assume that on average, we can look at it as if on average you neither lose or win, but then casino will take away some money from you. So it's like negative risk premium. So the gamble is no more fair, is no more actuarially fair. The gamble is actually unfair because the actually unfair because the risk premium is negative. Tell me please, what about investments? Is it actuarially fair or actuarially unfair? Let's call it also gamble, for example. Is it actuarially unfair or actuarially fair? And by the way, you might be guided by this graph. Well, actually, it is unfair, and don't be confused by these lines, because unfair does not mean always bad. Unfair only means that on average, you either on average the average outcome is not equal to 0. So that's what means unfair. But it can be less than 0, and it is unfair, and it can be more than 0, and it is also unfair. So in case of casino, it is less than 0, the average outcome. So it's unfair. Let's look at markets, and now again some stylized facts about stock markets, which you already know. That on average over long period of time, for example, here we have 1926, 2008, but this will be true just for any other long periods. So over a long period of time, on average, stock markets will give you larger return than, for example, where we have bonds, so treasury bills, this green line. So this difference is risk premium, and you can see it's actually positive. So it's also actually unfair gamble, but it's good for you in this case because actually you get premium, positive premium, not negative premium where you get away money like in casino. You get money. So, but that works only over a long period of time. So essentially, it means that just like gambling, investments is actually unfair gamble. Then let me see what I have here. Yes, this is I think what was mentioned by um, mhm. No, I cannot just find. Okay, Dunks, yeah. So indeed, when you gamble, you actually will get your results outcome. I don't know within a seconds probably. Just you need one roll or of a roulette wheel, and that's it. So you know the outcome immediately. There is no need to take into account time value of money. But when you invest, you don't speculate. You don't have a scapeler deals or something like that. You invest, meaning like there is some significant amounts of money for which you are going to hold the portfolio. In this case, you need to take into account some value of money. That means that your choice when you gamble, so your choice is not to gamble or to gamble. But if you go to the market, your choice is if you want to choose, if you choose gamble, it's just like choosing to invest into the stock market, a random outcome. But if you choose not to participate in the gamble, it's just like you do not invest into the stock market, but you can invest into risk-free assets, and then you will get money for sure. So this is something analogous to not participating in a gamble. You will not lose anything, but actually if you have this time value of money, if you have some time, then you can take money for sure. So that therefore recall that's why is our risk-free interest rates, and therefore when investment is not immediate in time, and therefore your average outcome if you don't participate is actually calculated like that. So it's not anymore simply your original amounts of money. It's your original amounts of money plus some interest. And then okay, outcomes. Obviously, stock market does not offer you just it's not a binomial gamble. It has many outcomes, but this is actually very similar to casino roulette will because there are also many outcomes, so it's not problem very significant. This is actually not a difference. I don't know why I put it like that. Okay, but anyway, this is not there are no binomial outcomes. There are many outcomes. So we have no, we don't have anything else. But actually, if we come back to what, so there was something about predictions, but I cannot find it now. Okay, forecast. Well, I like this, this forecast, meaning that, but actually, I would say it's vice versa. In case of casino gamble, if you know the rules of the gamble, you can always calculate probabilities, right? But you not just calculate, you can calculate precise probabilities as long as you know the rules. And actually, that's what I ask you to do in your home assignments. But in case of investments, obviously you will be interested in what results you will get when you liquidate your portfolio. And again, you can only get some average, probability weighted average. And in this case, you need to find probabilities of each outcome in the future. But unlike in a casino, you cannot calculate precise probabilities. You can assign your own probabilities to different states of nature, to different outcomes, but this will be your assessments. True probabilities cannot be known, unlike as in casino. And probably the last thing is that in the market, you, or not you, but someone else can use insider information to trade. So even though it is prohibited, some investors still trade on insider information. But in case of casino, I don't think that it's possible to to use any kind of insider information. There is no such thing as insider information in case of casino. So that's the difference between gambling and investments. Important difference, but this difference does not change the mathematics. So the mathematics will be still the same. So you can use all these formulas, which we have here, to model risk aversion in the stock market. I mean, to model risk aversion for an investor rather than from a gambler, but for an investor. Now, another difference between gambling and investments is that in the case of investments, we usually think in terms, in relative terms, not in absolute terms. So probably in gambling, you will ask a question: how much money I would win if I'm lucky. But in investments, you would ask yourself or your manager, what's return I will get? So that this is something more convenient for us. So we think in relative terms, not in absolute terms. Therefore, even though here we have already calculated SCARA, which is the coefficient of absolute risk aversion, and it shows you your reluctance to participate in a gamble with them or in a bet with them absolute, where an absolute amount of money is at stake. But now let's derive another coefficient, which also shows your risk aversion, but this time to participate in a gamble with or in an investment or in a bet in a situation where a relative amount of money is at stake, because probably it's more corresponds to your way of thinking if you are an investor. So essentially, let's try to find out relative risk premium. So not the amount of money, but the percentage of return, additional return, which will make you to participate in investments. So, okay. But before, let's introduce some notation, which you already actually know. So this is, as usual, our risk-free rates. Then this is our random return. So Y is something which we'll get from investments into risk-free markets, into Treasury bill, for example, or UK Treasury gilts. And this is what you would get from the stock markets. So this is a random return if stock markets is actually fair. Recall that actually fair means that on average you neither lose or win. We already know that the market is actually unfair. It offers you premium. However, let's assume that it would be fair. In this case, random return would be like that, R. Well, on average, it would be equal to 0, but I'm sorry, on average, it would be equal to Y, because this is your alternative. But that would be fair market. So R could be different, but on average, it could be equal to the risk-free rate. This does not happen like that, but just this is our notation. Then this W0 means the initial amount of wealth. That is what you have right now. Then this is what you would get if you prefer not to participate in investments, meaning in risky investment. That is, you would go to the risk-free markets, you would buy treasury bill. In this case, that's what would be your outcome of not participation in risk investments. Then if you participate in risk investments, you would get this kind of return, which is random. So this return is constant, is fixed, is known in advance. This return is random. And we already know that actually under these conditions, no one would prefer get this return, because you will get rho equal to 0 on average, but then you might win or you might lose, but on average you actually can get this. So you would probably prefer this. Therefore, in order to induce a risk-averse investor to participate in the stock markets, we need to add again the premium. So that's why we have on here. So to some basis we offer additional risk premium. Okay, I got disconnected once again, and let me switch on the presentation. So I hope now you can see it, and it's weird a little bit. Okay, let me continue now. And actually was not, we have finished with the slide. Okay, so in order to induce our risk-averse investor to participate in a risky markets, we offer a risk premium. So I put this star sign here. So this is our star sign, just to show that this is going to be a percentage risk premium, not absolute amounts of money as we found before, but percentage or relative risk premium. And now probably we are more interested in this term rather than in absolute risk premium. So let's now what we're going to do now. Let's just run through the same kinds of logic, through the same kind of derivation in order to find out how to calculate a relative or percentage risk premium. So because this is something which we are more interested in investments when we invest into the stock markets. And again, as before, we use Taylor series approximation. So this time we approximate this function. So function of the end of period wealth. So 1 means end of period wealth, 0 means beginning of period wealth. And about what we approximate about our average wealth. And mind it's that in case of investments, your average wealth is not anymore just what you have before you move into the stock markets. Actually, instead of moving to the stock markets, you can move to the risk-free markets, and therefore your outcome, if you don't participate in the stock markets, will be your risk-free rate. So this time it's a little bit different. And now, so now let's just use this Taylor series approximation. Okay, let's do it like that. So I think I don't have this formula for the Taylor series approximation anymore. So I just start with the with the derivation itself. So this is our function. This is our end of period wealth, and that's how we calculate end of period wealth. So our random return from the stock markets. This is our random return plus percentage premium, and so this is what we will get at the end of the investments, and this will be a random outcome because this return is random also. And now we expand this according to the second order Taylor series expansion, but we use only second order. Yeah, you can see here. But let me erase it. So we can use second order term here. So second order Taylor series approximation. Let me switch on marker again. So again, you can do this. I think that there's nothing to explain. So this is our function self, then this is our first term, and so I wonder how I got it. I think it's given in lecture notes. I don't see. Well, anyway, I believe this should be correct. I derived it and it should be correct. So seconds. Okay. So these are, yeah, this is correct. So this is our first term. I could not see, the brackets. That's why I like to alternate square brackets and figure brackets. So this is our first term. This is our second term, like that, and this is our third term. Now I can see it. Okay. And so what we can do now, we can just again, we can take expectation of these parts of the left hand side, and now we take expectation of the, so let's put like that, and we can take expectation of the right hand side as well. And mind it's again that this is something which can be calculated because everything is known to us. This is your return from investments into the risk-free markets. So therefore, this is a constant known to you. So therefore, its expectation is equal to the constant itself. Then here, the only thing which is not known to us is this one. So return, and so we can just put expectation of it here, and then it will go here. And then I think I just have opened the brackets here, and then I'll get this expression. And then again, you have to open the brackets here, and here we have squared. So before you get open the brackets here and have expectation of each of these term, you will have to square brackets here. And so when you do this, again, this is given in lecture notes, the derivation itself, I think there might be one or two intermediate lines between these two formulas, but here I just save the time and space. Anyway, you will get the expression like that after you put expectation and then see how to get expectation if you have square terms. So now I'm going to take this expression and put it to the next slide like that. And now I'm going to remove some rubbish from this formula. I guess this is a kind of rubbish because I decided to remove it. Well, what is my motivation for this is just because, again, we have a squared term here. So rho is given in percentage, so it's a small. If you express it in decimal terms, that will be a small number, but then the square of this number will be even smaller. So just for simplicity, let's remove it. Otherwise, we will get a very difficult formula. Again, we just want to know how to calculate rho star. So this is our percentage return, additional excess percentage return. So again, we need to get some formula. So we need to simplify it. And therefore, this will be a negligible term. Now, again, if we express premium in decimals and expected return also in decimals, then their multiplication will give you a very small number. So let's just neglect it. And therefore, we just neglect the whole term like that, and then what? So I have the same here. Here I have a simplified equation, which I'm going to simplify even further. And this is the same. The second term is the same. So and again here we still have the squared term, but so we have expectation of the squared term. So in this case, if we open this squared term, if we open the brackets, then if we manipulate a little bit, then we will come to variance. Again, the manipulation I think is either given in lecture notes, or at least I'll give you a hint how to manipulate with this expression in order to get variance. Probably there will be just a hint because you need to know how to make these derivations yourself. You need to train yourself. So like that. Anyway, as you can see, we have come to this expression. Now we need to simplify it even further because it's still, well, it's still too big. So let's see what we can do with this. Again, we use our equilibrium condition. Recall that we need to assign risk premium, this time in percentage. And this risk premium should be set, should not be too big, should not be too small. It should be set in such a way that the utility from not participating in the stock market, so this is the utility from going to the risk-free markets, should be equal to the utility from expected utility from going to the stock markets, having a return, random return, plus this premium, which makes the stock markets unfair gamble. So this is what we have here. No, sorry, no, not that. Let me remove it. Actually, it's just the other parts. So this is this one. And so therefore, let's substitute this instead of this, like that. So I put it here, like that. Again, we can just nullify this, and we will get 0 here. And now we get the expression which is simpler, like that. And now we see that we have a rho star, our percentage premium, as a linear term. We don't have a square term here. I mean, we do have a square value, but you see we can just divide by wealth, initial wealth, and then we come to linear term. But generally, this is a linear equation, and therefore we get just one root for this equation or one solution for this equation, and that's how it looks like. So this is how we can calculate a relative risk premium. Let's probably now compare relative risk premium and absolute risk premium. So if we want to calculate the relative risk premium, we have half variance of return. If we want to calculate absolute risk premium, we have half variance of wealth. So this is ends of periods return, and this is ends of periods wealth. So that's the only difference. And then also we still have second order derivative divided by the first order derivative with this minus sign, minded that second order derivative is negative, and this minus sign makes the whole expression positive. But also additionally, we have this, W0 here. So this is our initial wealth. So that's the difference. But as for the interpretation, it is the same. We can say that the percentage or relative risk premium increases as variance of return increases, which makes sense. And also, this is still the curvature. So this is curvature. And again, we can say that as normalized curvature increases, so as we have something like that, then the risk premium also increases, which is kind of obvious. Probably you don't see this. So this is our wealth. This is our utility. So the more curvature we have in the utility function, the larger will be the distance between the straight line, which represents expected utility, and this curved segments, which represents the utility of certain amounts of money. So, this difference. So this is the difference. It will be larger, and therefore, the larger the premium will be. So anyway, so what we have here? One more thing, it's about coefficients of relative risk aversion. So this time it's called CRA. So it's not like CRRA, it's just CRA. So we have CARA and we have CRA. And CRA is also a kind of coefficient, but recall that CARA is calculated like that. Second order derivative divided by first order derivative, but this is CRA, so it's calculated like that. So we have CARA in the absolute risk premium calculation, and we have CRA in the calculation of a relative risk premium. And now I will ask you the same question. So we already know that normally for a rational investor, CARA is decreasing in wealth, but CRA is also a function of wealth. So this is a function of wealth. And now my question is, so what do you think about CRA? Do you think it should be normally decreasing in wealth, increasing in wealth, or it should be constant in wealth? So this is my question to you. Okay, increasing. So what about other students? Do you all agree with that it should be increasing? Okay, shall we assume that it should be constant? So Maxim, can you explain why it is increasing? Okay, you can think, but anyway, the correct answer is that most frequently it is actually constants, though sometimes it can be decreasing, and that will also be okay. Let's come back to the same example with money. So assume again that you have 100 pounds, and I offer you the same bet, but this time it's not about absolute amount of money which you can either win or lose. It's about relative amounts of money. So that was $50 or 50 pounds. So this is 50%, right, of your initial wealth. So 50% of 100 pounds. So if you win, I will give you 50%. And if you lose, I'll take 50% of you. And you still need to feed your kids and wife. So definitely you would not agree to participate. Now, assume that, or I'm not sure, I guess I did not ask you this question, I asked someone else. I think it was Victor, but anyway, doesn't matter. So this time, assume again that you have 1 million pounds, and I offer you the same gamble. If you win, I'll give you 50% upon your wealth, and if you lose, I'll take away 50% from your wealth. So what do you think? Would you agree or not? Mm-hmm. Right. You can imagine this. So in this case, if you lose, I'll take actually 500 million. Oh, you have 1 million, so I'll take 500,000 pounds from you. Well, this is not the same as taking away 50 pounds. This is much more, and therefore you would be more reserved to participate in this kind of gamble. But actually, assume that you have 1 billion pounds and I still offer you the same gamble. Would you now agree to participate? Just these two guys who answered. Can you answer once again? So you had million, now you have billion. But you now doubts. You have some doubts. Zhao, what about you? No, I'm saying that if you lose, I'll take half of your 1 billion away. It's not that we're talking still about 1 million. Still not. But I think you already I think you start doubting. But actually, if you have, for example, 1 trillion pounds, 1 trillion, so million, billion, trillion, 1 trillion, still not. Okay, the same. So Zhao, you. Okay, so you can see for you, Zhao, CRA is constant, but for Victor, I think I'm not sure how to interpret it, but I guess sure meaning that you would participate. So your CRA is still decreasing, but not that much as CARA. So empirically, it is found that for people CARA is definitely decreasing, but as for CRA, it's either constant or it is decreasing, but just slightly, not that much as CARA. So that's what is found empirically, and that's what we actually have demonstrated just using 2 students only. Well, that's just an example. You can read it at home. Well, that's it about this particular topic about risk aversion and some utility function. We won't go any further, and you will have home assignments about all this. However, we still have more time. We still have about 17 minutes, and I would like just to start another topic. Let's not waste time. And now we are going to switch to the portfolio theory. Tell me, please, have you studied the portfolio theory in this course? I mean, in this master's program, probably in some other course. You know, this Markowitz portfolio theory. No. Okay. Somehow I felt that you studied it already. Okay. Very little. So what I suggest, actually, the portfolio theory is not that simple, and I'm going to actually, this is what I do even for students, you know, this from the SUF program, strategic finance program. I usually narrate the portfolio theory at a primitive level, meaning like it's a level of bachelor course, and then I retell once again, narrates once again the same topic as a master course, because it's a master course, it's kind of complicated, and if you don't know it at a bachelor level, you might get lost. So I will just start narrating the theory, the portfolio theory at a bachelor level. That's going to be really easy. And then I will start now, finish next lecture, and then at the next lecture, I'll start the narration at the master's level. So for this, let me first of all open the find the presentation. Куда ты все делся вообще уже? Ой, ничего не понимаю. Нет, так я не хочу. Tell me please, what do you see now? Okay, this is good that you don't see anything, because I wouldn't like you to see my desktop. Now, wait a second. I need to open this bachelor's level presentation of the portfolio theory. Okay, I'll just take this demonstration from SUF program. I think it's okay. Okay. Okay, so let's start. Probably, like, you know, probably we'll be able to discuss 3 or 4 slides, not more, but still. So actually, sometimes it's called mean variance model. Actually, this is portfolio theory model, but sometimes it's called mean variance model. Why it can be called mean variance model? So mean means mean return, or variance means well, variance or return. Sometimes, and this is really funny, sometimes students believe, and actually that's what they write in their master's thesis, they actually believe that this is kind of average variance. Mean variance means average variance, but this is just really funny, because mean means mean return and variance means variance of returns. So why it's called like that? Because we assume that we can represent it's enough for us. If we want to create a portfolio for our clients, it's enough for us to express everything in terms of mean and variance. So we don't need to know any other parameters. And then you will see why this is so. And actually, this is kind of a plausible assumption. This is not something very unrealistic. I mean, sometimes portfolio theory, I mean, some modern students, they can say something like that, like, why do we study? The portfolio theory is 70 years old or 60 years old, I don't remember. So there are other models which we can study, but actually I believe that the students who say this, they just don't want, they are too lazy, or probably they don't have enough intellectual ability to study this model. Because in fact, you might be surprised, but this is just if people don't know this. But even up to now, and European asset managers and wealth managers and American asset managers and wealth managers, they still use the portfolio theory as their working horse. That has been proved by many modern research papers. This kind of research papers where research is done in terms of questionnaires. So researchers send questions to asset managers like, do you use a portfolio theory model? Then how frequently do you use it? Something like that. And then they just generalize all answers and make conclusions. So the mean variance model is still the working horse in the asset management industry and in the wealth management industry. You probably know the difference between wealth management and asset management. So, and that's why we're going to study it also. Anyway, so you can create a portfolio for your clients if you're an asset manager based on mean return and variance return. Mean return means that you don't really know what return will be from the portfolio, because that will occur in the future. So right now you can only calculate average or mean value. So that's why you can calculate mean return of your portfolio, and you can calculate variance of the portfolio. And now, so this is our mean return and variance. Variance actually, sometimes you can express it in terms of variance, but actually it's standard deviation. So, it's square roots of variance that we use. In any way, this is volatility. Volatility is either standard deviation or variance, and volatility means risk, uncertainty. And usually we actually work with the standard deviation rather than variance, but somehow it's called mean variance. We don't call it mean standard deviation model, we call it mean variance model. So now this is what we have, and this is our utility. Look at the graph to the left. So this is our utility, this is our wealth, and this concave function is the utility function for risk aversion. Convex function is the function for risk lever, and this straight line is the function for risk neutral investor. As I said at the very beginning of the course, the majority of investors are risk averse, so we are going to model mean variance portfolio for this kind of investor. Just we consider this risk neutral and the risk lovers just for the sake of some diversity. We won't go deep into this, but just for the sake of diversity, let's look to the right. And here we have another plane. Plane meaning, well, the system of the coordinate system. This is a plane. And this plane now is featured by different axes. So here we measure expected return on the portfolio, and here we measure risk of the portfolio. So within this plane, we can also present utility functions of our three types of investor. So risk averse, risk neutral, and risk lover. And they will look quite different from one another. And let's see how they look like. So if this is a risk averse investor, then his utility in another plane, in a plane measured by expected return on standard deviation, would look like that: either this dark blue line or pale blue line. Just two versions. Actually, this is not utility. Strictly speaking, this is not utility because we don't have neither axis is measured as utility. actually this is indifference curve. I guess you know what the indifference curve is. So here in this plane we have utility, but what corresponds to utility in this plane is utility indifference curve. So this is indifference curve. A risk-averse investor would require more return, expected return, as he or she encounters more risk. Therefore, it's increasing. Just two versions, meaning that the dark blue investor is very conservative and pale blue investor is less conservative, but they still are both risk averse. Then, as for risk neutral, he doesn't care about the amounts of risk, so he just only look at the expected returns. So even if we increase the level of risk for the portfolio, our investor who does not care about the risk will require the same return. So therefore, we'll have this dashed horizontal line. And as for risk lover wants more risk. So he is ready to sacrifice return in order to get more risk. So therefore, we have this decreasing shape. Well, anyway, and by the way, you know that indifference curves, if you have ever studied indifference curves, you know that they might, when they shift, we generally shift to a better level. We become better off. So the question is, where should we shift our indifference curve in order to be better off? In our particular case, we shift them in this direction. So this is, well, I would say northwest, right? This is northwest. So we move to the northwest, and in this case, we become better off. This is quite obvious. So if we shift from this curve to this curve, then for the same amounts of risk, right? For the same amounts of risk, we can we have a higher return. This is definitely great. So just remember this. If we want to be better off, generally, if we want to improve our situation, then that means that we shift to the northeast, something like that. And so let's summarize. Utility is that if we move to the northeast, that means that utility is directly dependent upon mu or me. Directly dependent means that there is positive dependency. The larger the expected return, the better the larger utility we will have. At the same time, we don't, if we are risk averse, we don't like risk. By the way, so this is standard deviation, but you probably know that volatility, not volatility, variance is described like standard deviation squared, but actually this, if we have 2i here, this is also variance. So that's how I just denote it. So this is standard deviation and this is variance. Anyway, there will be an inverse relationship between utility and risk. We don't like risk, so if we have more risk, then our utility decreases. So how much time we still have? 4 minutes. Okay, then let me move to the next slide. And at the bachelor level, we usually discuss the portfolio which consists only of 2 assets for simplicity. Next time, we consider a portfolio which consists of many assets. And therefore, I will ask you to refresh your knowledge of matrix algebra once again, because we are going to use matrices. But now we are fine with just one equation. So this is the weight to assets I, this is the weight to asset J. This is all our money, so in total they are going to be equal to 100% or just 1. And therefore, weights for asset J can be expressed as a linear function of weights for assets I. Then the expected return from our portfolio is just, expectation is a linear operator. Therefore, we just, the expectation of the sum is equal to the sum of expectation. So this is our expectation, and then plus expectation of another return from asset J and return from assets I, weighted. So weighted average, and so that's what we have. That's how we calculate expected return for our portfolio, which consists only of 2 assets. Variance is a non-linear operation, so we have variance, and plus we also have 2 covariance terms. Well, this is just econometrics. This is constants. This is also constant. So then we just remove constants from the brackets and we'll get squared theorem. And this is also covariance. And this is what we have. Mind, it's again two letters in the index means that this is variance. If I had only just one letter, then it will be standard deviation. And this is our covariance theorem. Now, let's look once again at expectation and variance. Actually, both expectation and variance are dependent upon the same variable. And this is weights given to assets I. Actually, it's dependent upon two weights given to assets I and weights given to asset J. But if we can express weights given to asset J in terms of weights given to assets I, like here, then for simplicity, we can say that both two equations are dependent upon weight given to just one assets I, for example. Therefore, this looks like a system of parametric equations, and probably you can recall from school how to draw these kinds of equations geometrically. But what we can actually do, let's look here. So essentially, we would like to draw an equation where here we have variance, or to be more precise, standard deviation, actually. And here we have expected return. So we have two equations. They are the same. They are dependent upon the same weights. And so what we could do, you can actually try to do it at home, but that will be a little bit complicated. So try to express. So this is our importance variable. So this is what this is from what upon what expectation variable are dependent. And therefore, we can actually use this linear equation. So this is our linear equation. You can take and you can try to express weights in terms of expectation. So just reverse the formula. And then you will get some expression for weights. And then take this expression for weights and put it into this variance expression. So here. So if you do this, you will come to a quadratic equation. You can try it at home, but this is complicated, else it's complicated. But then, anyway, you will come to quadratic equation. And now tell me, please, how many types of quadratic equations do we have? So recall from mathematics. So yeah, the same question. How many types of quadratic equations do we have? Okay, I'll give you hints. Well, I'll give you an answer, actually. We have three types of quadratic equations. Ellipse. Then what else? One is ellipse. Other is parabola. Oh, wait. No. Not like that. Only three. So ellipse, parabola, and hyperbola. And in our case, if we do all these substitutions, we will get a hyperbola because whether we will get ellipse, hyperbola, or parabola depends upon what coefficients we will get. But in this particular substitution, we will get coefficients in such a way that will come to hyperbola. And you can see this hyperbola. Actually, hyperbola looks like that. So it's symmetric, but whatever happens here we have negative standard deviation, so economically it has no economic meaning. Therefore, we are going to work only with the right hand side of hyperbola. But that's what we are going to discuss next time, not today, because we are going to finish right now. And my last question is, tell me please, are you all in Moscow or you are still somewhere far away? Should we switch to the offline modes? Far away, do you have any possibility to come to Moscow?
I wish, but the visa center don't issue student visa now.
So do we have only two students who are far away. What about the rest of the students? So will you be able, and where are you now staying? Which country? My question is, so I guess it's not possible for us to switch to offline modes because I think that's what I'm going to do with other students, but not a problem, I guess. Because of our Chinese students, we cannot do this here. But I would like to conduct the final test offline, not online, because I don't like this, when students take online test. So, Tell me, please, do we have students apart from 2 Chinese students? Do we have other students who are not able to come and to have offline final test? So we'll be able to come to the to a classroom. Okay. So I think that if there are some students who cannot, they would probably say this. Maxim, so what about you? Was be able to come to Moscow for the final test? Yes, it's needed. Okay. So I believe that probably we will have a chance to you will have a chance to sit the final test offline. That will be just better for you and for me as well. And for Chinese students, probably it will be possible just to conduct simultaneously somehow online with the same questions. But unfortunately, it's not possible for us to meet offline before this. Looks like that. So in this case, we will still stay online, and next week I'll see you online in this case. So next week you will have 2 tutorials, and I'll send you home assignments and lecture notes tomorrow. And for now, that's it. So I'll stop the demonstration and say goodbye to you and have a nice weekend. Goodbye.